Today we're going to talk about how to compare two numbers. In particular, the example we're going to use is to compare 2 to the power of square root of 3 versus 3 to the power of square root of 2. Which one is larger, which one is smaller? And we're going to do it in two ways. One way, we're going to use algebra tools. The second way, we're going to use calculus tools. But no matter what way we're going to do it, we need to actually do some transformation to these numbers. And by transformation, I mean applying some kind of functions to the number on the right and number to the left. And those functions are normally monotonic. To understand how to do comparison correctly, we need to know what monotonic functions are. So today we're going to talk about two types of monotonicity: monotonically increasing functions and monotonically decreasing functions. Well, technically we're going to talk about strict monotonicity. So every time when I say monotonic, I really mean strict monotonic. But anyway, first of all, definition. What does it mean for the function to be strictly monotonically increasing? So if we look at certain range and we're saying the function is strictly monotonically increasing in that range of x's, what we need to do, we need to pick up any two values, x1 and x2, from that range, such that x1 is less than x2. And if you find that for any such x1 and x2, f of x1 is less than f of x2, we're going to say this function is monotonically increasing. The inverse is also correct. So if you know that function f is strictly monotonically increasing, and you know that f of x1 is less than f of x2, from that it follows that x1 is less than x2. Some other interesting properties of monotonically increasing functions. If we pick up really any function g of x, and then we're going to apply our monotonically increasing function f to that function g of x, and we want to see the behavior, you'll find that behavior of g and f of g qualitatively is the same. So wherever g of x is increasing, f of g of x also going to increase. Wherever g of x is decreasing, f of g of x also going to decrease. Wherever g of x is minimum, f of g of x is also going to be minimum at the same point. And wherever g of x is maximum, f of g of x is also going to be maximum. Strictly monotonically decreasing functions do the opposite. So whenever x goes up, f of x goes down. So for any x1 less than x2, for strictly monotonically decreasing function, f of x1 should be greater than f of x2. The opposite again is correct. You have f, which is strictly monotonically decreasing function, and you know that f of x1 is less than f of x2. From that it follows that x1 is actually greater than x2. If you have again g and f of g, the behavior is completely opposite now. When g goes up, f of g goes down, g goes down, f of g goes up, g has minimum, f of g is going to have maximum at the same point. G is maximum, f of g is going to have minimum at the same point. Now let's look at examples of monotonically decreasing and increasing functions. Obviously there are infinite number of functions like that, but some of them are used more often than the others. So let's consider the functions that are commonly used. For monotonically increasing functions, first of all, exponential function. A to the power of x, as long as a greater than 1. This is monotonically increasing function. Logarithm, as long as the base greater than 1. This is monotonically increasing function. Power function, x to the power of a, as long as a is positive and x greater or equal than 0. Another example is linear function, cx plus b, where coefficient c, which is slope of linear function, is positive. It is also monotonically increasing function. The linear function is an interesting function. In school, we were told that when x1 is less than x2, and we multiply both parts by a positive number c, inequality holds. If you add any number b to both left and right side, inequality still holds. That's what we were told at school. But now you can simply just take the first line and take the last line and simply say, well, the last line is an application of a linear function with positive slope to the numbers x1 and x2. And that function is strictly monotonically increasing, and it should preserve the inequality. Now, if you go to monotonically decreasing functions, really the same functions, but in a different range of the parameters. So exponential function is going to be strictly monotonically decreasing if the base is between 0 and 1. Logarithm has the same property. Power function is going to be monotonically decreasing function if a is negative and x is positive. And the last one is the linear function with the negative slope. And again, we can compare what we have here with what we learned in school. We start with x1 less than x2. We multiply by a negative number c. We were told in school that inequality is going to flip in this case. Then we're going to add any number we want, and inequality holds. Now we're going to say that this last line is really application of monotonically decreasing function to this line. And obviously in this case, inequality has to flip. And now let's go back to our problem. We want to compare 2 to the power of square root of 3 and 3 to the power of square root of 2. First way we're going to do it using algebra. First, let's deal with square root of 3 and square root of 2. Notice that 3 is less than 3.24. That's obvious. Now what we're going to do, we're going to apply a square root to both parts of this inequality. Square root is a power function. It's monotonically increasing. So if we apply it, inequality will hold. But now we see that square root of 3 is less than 1.8. In a similar way, we can show that square root of 2 is greater than 1.4. Now what we're going to do here is we're going to apply an exponential function to both parts of this inequality. We're going to use exponential function with the base 2 to the x. And since this is monotonically increasing function, inequality will hold. In a similar way, we're going to apply 3 to the power of x to this inequality. And inequality will hold because 3 to the x is monotonically increasing function. The next thing we're going to do, we're going to compare 2 to the power of 1.8 and 3 to the power of 1.4. What we're going to do is them, we're going to take them both to the power of 5. Inequality is going to be preserved. Whatever we have here, we have here, because this is a power function applied to positive numbers. It's monotonically increasing function. Now what we're going to do here, we're going to apply this property of the exponential functions, that a to the power of b to the power of c is equal to a to the power of b times c. On the left, we're going to have 2 to the power of 1.8 times 5, which is 9. On the left, you're going to have 3 to the power of 1.4 times 5, which is 7. So now let's compare 2 to the 9th power and 3 to the 7th power. The way we're going to do is, first notice that 8 is less than 9, but 8 is 2 to the power of 3, 9 is 3 to the power of 2. Now we're going to cube both parts of this inequality. Cube x cubed is monotonically increasing function, so inequality holds. Again, applying this formula, we're going to get that on the left you have 2 to the 9th power, on the right we got 3 to the 6th power. If it takes 3 to the 6th power and multiply by 3, the number is going to increase. And now we have it. 2 to the 9th power is less than 3 to the 7th power. So here we have this inequality. That means that here we have same inequality, and here we have the same inequality. And now look on the left, look on the right, and we see that 2 to the power of square root of 3 is less than 3 to the power of square root of 2. let's do calculus now. Again, we can't really do calculus right away. We need to do something with these numbers. We need to apply some kind of transformation. And what we're going to do, we're going to apply natural logarithm to both parts. Natural logarithm is monotonically increasing function. So whatever inequality we had here, same inequality going to be here. Now, if you remember the property of the logarithms, that allows us to take exponent and pull it out of logarithm, we'll apply this. The next thing we're going to do is we're going to multiply both of these numbers by 1 over square root of 3 and 1 over square root of 2. By multiplying numbers by a positive number, inequality holds. But if you do what I said, we're going to have logarithm 2 over square root of 2 on the left and logarithm 3 over square root of 3 on the right. Now we introduce a function, logarithm x over square root of x, and we see that what's on the left is the value of the function at the point 2, and what's on the right is the value of the function at the point 3. And the last thing we need to do, we need to find the behavior of the function when x goes from 2 to 3. And for that, we need to take a derivative. But before we do that, let's look at function f as the product of two functions g and h. G will be logarithm x, and h will be 1 over square root of x, or in other words, it's x to the power of minus 1/2. Derivative of the function, which is a product of functions, is derivative of g times h plus derivative of h times g. Derivative of g is 1 over x, derivative of h is minus 1/2 times x to the minus 3/2. It's a derivative of a power function. Now if you plug these values are right here and kind of combine like terms, we get our derivative as x to the power of minus 3/2 times this parenthesis. We like to find where this derivative is positive, negative, and 0. First notice that x to the power of minus 3/2 is positive when x is positive, and that means that the sign of the derivative is defined by the sign of this parenthesis. And what we have here is actually we have a natural log, and then there is a linear function with a negative slope of minus 1/2 applied to our log function. Logarithm is monotonically increasing function, but a linear function with a negative slope is monotonically decreasing function. So when you apply monotonically decreasing function to monotonically increasing function, you're going to get monotonically decreasing function. And that's what we have here. Now let's see where this thing goes to 0. To see where it goes to 0, we need to solve this equation. This equation is equivalent to this equation, and we can quickly see that x star should be e squared. And that's the point where this parenthesis becomes 0. The next thing we want to do, we want to estimate where this x squared is compared to 2 and 3. Well, we know that e is about 2.7. It's a little bit more than 2.7. But for us, it's sufficient to say that e is greater than 2. Now we're going to square both parts of this inequality. We can, because x squared is monotonically increasing function, as long as the argument is positive. And we see that x squared should be greater than 4. Now, let's look at our number line. Here the point e squared. And since this function is monotonically decreasing, it means that on the left is going to be positive, on the right is going to be negative. And therefore the function f prime is going to be positive on the left and negative on the right. The positive derivative means the function f is increasing. Negative derivative means function f is decreasing. It means that function f achieved the maximum value at x equals to e squared. But we're interested in points 2 and 3, and they're right here. And we see that when the function goes from 2 to 3, it's increasing. And that means that f of 2 should be less than f of 3. That means that sine less is here, sine less is here, sine less is here, sine less is here. And we're done.